Yeah.
All right, good afternoon, everyone. It's kind of muggy in here, but I think we'll be okay. It's my pleasure to welcome you all to Dr. Kara Lamb's lecture in climate data science today. She is an associate research scientist at Columbia University's Department of Earth and Environmental Engineering. She is a senior researcher at LEAP, and her research develops physics-informed machine learning methods to improve understanding of atmospheric processes and their influence on climate. Her current work focuses on cloud microphysical processes and aerosol cloud interactions. Kara received her PhD in physics from the University of Chicago, and she was previously a research scientist at Ceres NOAA, where she was on the science team for the NASA Chorus AQ and ATOM aircraft campaigns and the NOAA FireX FireLab study. So, Kara, it's my pleasure to welcome you. Thank you.
This is fun. Okay. Great. Okay, so thanks everyone. Today I'm going to be talking about automating parameterization development for Earth system models with agentic AI. And so this is definitely still work in progress. So I'm going to talk about some things that are working well and other things which are not working so well. And I'm very curious about your feedback as well on this because it's definitely still something in progress. Okay. So just for motivation, in Earth system models, we have to make some trade-offs in terms of the resolution of the model, as well as which processes we represent and at which scales. So in typical Earth system models, we generally have processes that are going to be unresolved that we are going to have to come up with some simplified models or parameterizations for to represent what's happening at the subgrid scale. So there are all sorts of different parameterizations in Earth system models for atmospheric processes, as well as ocean processes, as well as land processes. And we know when we look at uncertainty in future climate projection, at least over the next 20 to 30 years, the uncertainty in these physical parameterizations is still what is going to be dominating in terms of our uncertainty in future projections. And then in the longer term, the emission uncertainty is really what is playing the dominant role. And because parameterizations are still limited, there's been a lot of recent work in the last, say, 10 years on using machine learning methods to try to improve parameterizations for many different processes, which is a lot of the work that we have been doing here at LEAP, is developing machine learning methods to improve different parameterizations or replace parameterizations with machine learned based parameterizations for processes. And would say since about 2018, there's been this revolution in terms of moving away from just emulating specific processes of specific subgrid scale processes to actually modeling the entire atmosphere or even the coupled atmosphere ocean. And we have seen that starting back in 2018, if we compare the skill of these AI weather models with the state-of-the-art numerical weather prediction model from ECMWF, we saw back in 2018, they were not doing very well, but very, very quickly, we've gotten to the point where these state-of-the-art AI weather prediction models are actually doing better in some skill metrics than the numerical weather prediction models. So you might ask, if we could just emulate the entire atmospheric model or even the coupled or system model, do we actually still need parameterizations? And I'm going to say, yes, we do actually still need parameterizations because AI models are still mainly trained on reanalysis data sets, which have their own biases. And so if we want to continue to improve our Earth system models, our weather prediction, as well as our long-term climate prediction, we do need to be able to improve our understanding of the processes. And in particular for the climate case, climate is much more difficult than this shorter, 2-week timescale for weather prediction because it requires generalization outside of our training distribution from a machine learning perspective. So we can't simply rely on training on historical data when we're thinking about projecting future climate. So we still really need the physics-based parameterizations or more reliable parameterizations to ensure that our model projections will actually be reliable and realistic. And finally, if we want to connect back to our understanding of the Earth system, both historically as well as as we gain new understanding from process level models, from laboratory and in situ measurements, and remote sensing observations. If we want to be able to connect that to the large scale models, we also need these physics-based parameterizations. So I'm going to talk today about how there's promise to improve the whole parameterization development cycle. And the current way that we develop Earth system models is quite slow. I'm going to be somewhat biased towards the atmospheric parameterizations because that's what I know best. But generally for atmospheric observations, we might get new physical insights from field campaigns or from high resolution models like large eddy simulations or cloud resolving simulations. We have to do a lot of work to translate this physical insight into code that can be, or a parameterization that can be executed in models. And we have seen that machine learning can help accelerate that. But there's still this translation bottleneck where we're going from our whatever observations that we have that can have many different modalities to the code that we actually need to integrate into our model. And then there's another challenge when we have to take these new parameterizations and actually integrate them into legacy or system models, because these are often very large code bases. They're typically Fortran and or C++. In particular, for integrating machine learning algorithms, they are difficult to integrate because most of these are developed in Python or Julia or other libraries, like other coding languages besides Fortran and C++. So there's often this challenge of integrating our new machine learning parameterization into the model. Once we've integrated the parameterization into the model, we then have to tune. We do then have this tuning process and testing and validation. And the tuning process itself is something which has been described as both like an art and a science, because there are many sort of expert intuition and a lot of choices that are made in terms of which parameters we're choosing to tune, what observations we're comparing against. So there are a lot of these things are really reliant on expert intervention and intuition in terms of how we make the choices about how we even tune these models. And then, of course, running these complex code bases and iterating over them is something, this whole process is something which takes years to make major changes. So there is now, I think, potential to more systematically integrate new physical understanding into our system models. And this is because of the convergence of really two different developments that have happened in the last couple of years. There's been the development of agentic AI. So this is basically using large language models with multiple calls to the large language models, and with iterative tool calling and other iterative evaluations that allow us to actually have some decision making in our pipeline that we're automating. And this has been used for things like code translation, literature review, and potentially parameterization development and integration, which I'll talk about today. And agentic AI is being used in the last couple of years to now enable some complex scientific workflows. And the other main advance is the increasing use of differentiable programming. So differential programming in languages like JAX or Julia can allow for a fast and gradient-enabled test bed. So combining these two together has the potential, I will argue, to advance our ability to much more systematically create this process of parameterization, development, integration, and tuning, and the whole workflow of developing our system models. So as far as, I guess I'll talk a little bit more about agentic AI and its use as a scientific workflow engine. So we can call it, large language models like ChatGPT as with just single shot generation. But really, in the last year or two, there's been a lot of demonstration that agentic AI is more powerful when we kind of have this iterative tool using workflows with feedback. And with that, we can actually have the models reason and plan, or write and run code. They can analyze data and revise and iterate. And we've seen this start to be integrated into across the sciences. Like, for example, in laboratory sciences, they're being used to adapted to very complicated pipelines in laboratory sciences. And I think there's a lot of potential to adapt the same types of tools now to like these large-scale model development programs like Earth system models. And the other advance, like we've seen with agentic AI, is like there's been a lot of use of these methods towards the field of mathematics to solving problems that are can be quite challenging and require like multi-stage reasoning. And we saw back in July of 2025 that there was already demonstrated skill for some of these models at solving complex problems like gold level performance on the International Mathematical Olympiad. And there's been really a huge use now of a lot of these methods in the field of mathematics as well to like try to more systematically create proofs. So I would say this is like showing that there's a lot of potential that these tools are not just like they're actually doing something where we can potentially start to use them for like real science and real Earth system model development. In terms of like why differentiable programming, differentiable programming is when computational models are designed to allow for the efficient calculation of gradients with respect to model parameters using automatic differentiation. We can more systematically assess, like we can, with differentiable programming, unify our physics-based models and machine learning. And we can actually optimize parameters in both the physics-based models as well as the machine learning models. We can use differentiable models with gradient-based tuning. We can optimize parameters end-to-end using auto differentiation and adjoints, which we basically have for free with these models. We can then, this enables us to do sensitivity analysis on parameters. And the other major advantage, especially for using a language like JAX, is that these types of models are kind of very scalable for deployment on architectures like GPUs and TPUs. So this will enable sort of next generation development of Earth system models on like that are taking advantage of these newer hardware developments. So there are still like a number of unique challenges that when we're talking about automating Earth system model development. So we do have these large, complex legacy code bases. We do have to worry about hard physical constraints, as well as indirect observations and expensive simulations. We also know that there's very complicated nonlinear couplings, and there's a need for stability and interpretation. So these are all kinds of things that we need to start thinking about when we're thinking about setting up a workflow that could automate this process of developing parameterizations and integrating them into models. So I'm going to talk today about some work, which, as I mentioned, is still somewhat of a work in progress, but just thinking about how we could really create a workflow that would allow us to both automatically develop parameterizations and then integrate them directly into Earth system models and do this whole tuning process. I'll talk mostly about the automated parameterization development pipeline here. But the idea is that this would eventually all be implemented in JAX so that this could be like have a fully coupled Earth system model in JAX, integrating with some of the current developments like JAX GCM or Lego ESM that Pierre is leading. And so here I'm going to show some applications to warm rain cloud microphysics as sort of this like hello world problem for like, can we develop parameterizations automatically for collision coalescence? And just for motivation, collision coalescence is an important cloud microphysical process, and cloud microphysics is one of the processes that we have to parameterize in our atmospheric portion of our models. So cloud microphysics is something which still limits the fidelity of models, and this is basically showing many of the different processes that we parameterize in the atmospheric portion of our model. And cloud microphysics is something that we just have typically parameterized at the single grid box scale. And we have many different cloud microphysical processes. I'll focus here on collision coalescence as a sort of interesting use case. So collision coalescence is when we have, it's basically one of the major processes that leads to rain formation in clouds. It's going to affect how we parameterize it affects the lifetime of clouds, as well as like the amount of and timing of precipitation. So it is quite important for Earth system models to have this process parameterized correctly. And we have generally smaller droplets that will collide to form larger droplets, and then larger droplets that will fall through the cloud and collect smaller droplets. And so this is effectively the process that we are trying to parameterize. And why I think this is like kind of an interesting hello world type problem for automated parameterization development is that we have this 50-year lineage of published schemes with increasing complexity in terms of how this process has been parameterized. We also have a high fidelity ground truth that we can pretty easily access and create data sets for like testing and training parameterizations. So these high fidelity ground truth are based on things like super droplet or bin microphysics schemes, and these can be used to develop and evaluate the simplified bulk parameterizations that we use in our system models. And we know that there are structural pathologies in our current parameterizations of collision coalescence. For example, so like in a single model grid box, we have some, like what would actually be happening in the cloud is that we would have some complex distribution of smaller and larger droplets, and this can typically be bimodal. And a simple bulk parameterization would just have like a cloud distribution and a rain distribution that it would fit to this distribution in the grid box. And then we would just derive some bulk moments. And our typical bulk process rate would effectively be a coupled ODE that is going to be power laws of the cloud and rain moments. But there's different choices that people have made in terms of how they have chosen to parameterize this. So this very simplified set of coupled ODEs is what would ultimately go into the Earth system model to represent the subgrid scale collision coalescence process. But we can have much more accurate sort of Monte Carlo type simulations where we can explicitly simulate this process. So the current way that bulk schemes are generally developed is this more manual expert-driven process where we would say run a large eddy simulation with a bin microphysics scheme or a super droplet microphysics scheme. We would use that to determine the kind of ground truth, and then we would fit some different process rates that describe this collision coalescence process. And we might, in the traditional way, just assume a functional form and then just see which functional forms best fit the explicit, say, auto-conversion rates, and then fit specific parameters to basically best fit our LES model. And there's a number of limitations. We have this like assumed a priori droplet size distribution representation. The microphysical process rates have an assumed deterministic functional form, and we don't typically include things like memory of previous time steps. So this might be ill-posed for truly representing the collision coalescence process. And we also know that there is this, typically the threshold that people choose to distinguish between cloud and rain is something which is like known to be problematic, because we can't just have a single threshold for like a heavily drizzling or a lightly drizzling cloud versus like a heavily precipitating cloud. So in terms of looking at how agentic AI can be applied to this, I'm going to evaluate a couple of different things. One is just, can we reconstruct classic schemes in JAX using agentic AI? And can we reconstruct a couple of machine learning baselines, which are that have been developed in the last 5 or 6 years in terms of using machine learning to parameterize this process? And I will also look at how well agentic AI can do in terms of proposing new approaches or new closures. And I'm going to talk about sort of 2 different ways of doing this. One is like human in the loop development, where I'm using Claude code, and there's a lot of intervention by me to guide the system as it's developing the parameterizations. And then I'll also compare this with some single shot and iterative API calls to Gemini Pro, just to see like how well this compares to more of a more systematically to just single calls of a large language model or iterative calls. So I would just say I don't have a lot to say about this, because this is the Claude opus with expert in the loop development for just taking classic parameterizations, implementing them in JAX, and then comparing them like in how stable they are in rollout. And I would say like overall, this works like extremely well. The agent is able to implement historic schemes from the literature. So I'm just showing 4 examples here. It's able to reconcile different prognostic variables and set up a single common state vector, even though some of these schemes are based on just like a single moment and some are based on a 2-moment representation of the underlying like distributions. So This like does pretty well, and we get these like stable differentiable JAX native bulk microphysics library that we can develop. So I'm also going to evaluate the single shot performance for JAX-based LLM translation. So this is using that unattended API call to Gemini. And what I do here is I give the large language model a prompt and the original PDF and also a target interface, and then ask that it is able to ask it to create a JAX-based parameterization based on that paper. And then I do this 10 independent times. So it's calling the Gemini API independently 10 times, and there's no shared context. So it's basically just seeing how well, if I just give it a single call, like how well it can do. So here I'm just comparing how much source code is developed. The Gemini translations are the green dots here, and then the red is my handwritten, or I should say Claude plus myself handwritten JAX version of these 4 different schemes. And so we do see like across the 10 independent calls, there's is some variability in terms of how it's doing the translation each time and like how many lines of code it actually ends up with. But there is some similarities in general, like the less complex schemes generally have fewer lines of code. I then evaluated this sort of single shot JAX translation success across like 4 different metrics. One is for like if it actually runs the code. One is if the code that it developed was actually differentiable. The third is if it is mass conserving, because I gave this as a constraint to the model. And then the fourth is whether it can actually be stably rolled out over 6 hours in this box model simulation. And so you can see that this is actually somewhat parameterization development in terms of its success. And what is interesting is like Barry and Reinhardt was one of the papers that I gave this. And this is actually a parameterization that human implementation has actually faced similar translation ambiguity. So this paper was reviewing a number of different implementations of Barry and Reinhardt from 1974, and they found that only 3 out of the 12 different human-based implementations of this particular parameterization could actually reproduce the original bin model solution. So it's interesting that, I mean, the large language model struggles, but like even it's not necessarily that much worse than human translation of these parameterizations. Another thing that we can look at is like why the model is actually failing each time. So we have, so the Kessler and Krudenov and Kogan models like did quite well. They was able to pass all 4 of these criteria that it ran. It was differentiable. The resulting parameterization was mass conserving and that it was stable. But Barry and Reinhardt and Seifert and Beiheng were like more challenging for the model. And we can look specifically at why it failed each time, like which of the specific criteria it failed at. So like for Barry and Reinhardt, many of them were non-differentiable, whereas for Seifert and Beiheng, it was more that they were unstable, not that they were not differentiable. And let's see, we can also compare like their actual fits to the like expert in the loop build, and as well as the mixed snow, so like kind of a ground truth high fidelity simulation using a box model with super droplet. So that's the black line. The handwritten reference is my expert in the loop JAX translation with Claude, and then the Gemini translations are in blue for all of these different parameterizations. So you can see for like Kessler and Krudenov and Kogan, what Gemini produced with this single shot call was actually pretty similar, whereas like we do see a lot of variability in what it did for Barry and Reinhardt and Seifert and Beiheng. So it is interesting that we do see some parameterization dependence of like how well this type of translation can actually work. Okay, so the next thing that I looked at was whether we could reproduce some of the existing machine learning baselines for parameterizing collision coalescence with neural networks. So there's been a couple of papers in the last couple of years that have used neural network regression to try to learn an improved functional dependence for these bulk process rates by training on bin or super droplet simulations. So I'm going to show trying to reproduce Seifert and RASP, which was one of I think the first paper that tried this. And so Seifert and RASP looked at basically creating 4 separate MLPs. It's evolving these 4 separate MLPs for a single that are describing the ordinary differential equations for these like 4 separate process rates. And then it's learning to predict basically effectively the next time step with a forward Euler rollout. So I give, this was like expert in the loop development with Claude, and it's given access both to the paper as well as the high fidelity data that Seifert and Rasp like used in their development of the parameterization. And that consists of box model simulations with mixed snow super droplet microphysics is like the ground truth that it's learning the parameterizations from. So this is basically just showing how well my Claude like emulated like Seifert and Rasp warm rain parameterization work. This is just the single step prediction. And this was when I asked it to reproduce a figure from the paper, which is showing the stable rollout for the parameterization. So the ground truth mixed snow data set is in black. Seifert and Beihang, which is kind of one of the traditional bulk parameterizations, is in blue. Seifert and Rasp from their actual paper is in the lighter dashes, and then the redeveloped one using Claude code is the stronger dashed red line. So it's able to basically reproduce the same baseline given access to the high fidelity data. And the next tried to reproduce a more complex published machine learning baseline for collision coalescence based on this newer paper from Sharma and Greenberg. And this is the same. It's also expert in the loop development with Claude Opus, Claude Code. And the main difference with this parameterization is they have a much more complex training process in terms of how they set it up. They're actually doing this like autoregressive and curriculum-based rollout progressively over 25 time steps. So this was the training data set is very similar to the one that was used for the development from Seifert and Rasp. So this one was a little bit more complicated for Claude Code to actually reproduce. And I think that we're still not doing as well as like the original paper states. But this is basically, I asked it to reproduce this figure from the paper. And it's, so like the performance of their super dropnet model is still not doing quite as well as like compared to what it was given in the paper. Though it seems to do well at reproducing the architecture, but it really struggled with reproducing that complex training process. And I think this may also be due to the fact that how the training process was described in the paper may have been very challenging for Claude to actually interpret. This is another thing I'll talk about was like trying to develop a new physics-constrained neural ODE closure using Claude Code with expert in the loop intervention. So Claude Opus came up with some very interesting ideas that were like reusing ideas from historical physics-based schemes to constrain the machine learning architecture, like rate factoring rate factoring this state of this, as well as it did, by design, put in mass conservation, and also tried to set it up in a way that was interpretable. Although it did need like a lot of expert in the loop guidance for like going back and forth on this, and it's still like not performing as well as many of the other parameterizations, as you can see in the rollout. So the blue here is the neural ODE that it's come up with, as well as like the dash line is the ground truth that it's trying to learn how to predict. So there's still like, some work that could be done here in terms of actually improving, developing new closures. So I also looked at whether we can have an LLM come up with a new way to parameterize collision coalescence. I basically wanted to see if like it can be creative about coming up with new parameterizations. And this is going back to the unattended API calls. And so I'm basically giving it a prompt and access to the high fidelity ground truth mixed snow data set, which has been aggregated into 18 different variables, including the states that it's trying, the 4 moments that it's trying to learn to evolve. And I've told it there's kind of a, what's in that data set, as well as a certain number of design principles. And I'm going to call that 10 times and see how well these like invented schemes can pass in terms of how differentiable they are, if they're mass conserving, if they're stable, and if they pass all 4 criteria. So it was able to actually do fairly well with just the single shot at coming up with code that did actually run and was actually differentiable and mass conserving. And if we look at how this is basically showing the medium L2 error for the 4 different moments, the colors, these are different Gemini inventions compared to the Barry the Kessler is this blue line on the bottom. Then we have Barry and Reinhardt are these 2 red lines, and then Seifert and Bangheng. So the invented parameterizations did kind of fall relatively close to the existing parameterizations. If we look at the rollout, though, we can see that none of these invented parameterizations are doing all that well in terms of reproducing the ground truth. The next thing I looked at was if we could iteratively evaluate and improve these single shot calls. So this is again, given access to, this is doing single Gemini calls and then giving it access to high fidelity data, and as well as iterative feedback on how well the model is doing, the invented parameterizations are doing on those 4 metrics, if it's differential mass conserving, stable over 6 hours, and if it actually runs. So when it was given iterative feedback, it was actually able to create get all of the schemes to pass on all of these 4 criteria. So the iterative feedback is definitely improving the parameterizations over time. And if we also look at sort of the comparison to the bulk schemes, we do see that the overall error has gone down as well between the mixed snow accuracy, as well as the across the 4 moments. And we do see, it might be a little hard to see, they're the green lines here are the iteratively improved parameterizations, and they do tend to get closer to the actual rollout for the true mixed snow data set for this particular iteration. So iterative feedback is definitely helping the model to improve its ability to develop parameterizations over time. So another question that we might ask is how creative is it actually being and proposing these new bulk schemes? And I'm showing here basically these 18 different variables on the x-axis. The top 4 are showing which of these 18 variables the canonical parameterizations use. And the middle blue ones are these individual 0-shot or single shot calls to the API in terms of which variables it used. And then the blue is showing the iteratively improved feedback for which of the variables it chose to use in its parameterization. So one thing that we notice with the iteratively improved and the single shot is that none of them are including the density row in these parameterizations, even though the majority of the canonical expressions do include this. But I would say the jury is still out. We do see that there are differences in terms of which variables it's using across these different selected cases as well. So it is maybe coming up with interesting and creative new parameterizations, but it's unclear that any of them are actually doing better at this collision coalescence process. And so finally, we can, one of the last things I wanted to look at was can we systematically compare parameterization? So I think with these approaches, there's the potential to much more systematically look across various parameterizations and try to understand by comparing them all across the same data sets, how well, which of the parameterizations is actually doing best. This is showing 2 different metrics. This is showing the when 10% of the rain had been converted, or 10% of the droplets had been converted into rain, what that time scale is. And I'm showing sort of the classical parameterizations on the left. And I've taken the typical parameters in these parameterizations, as well as retuning these parameters on the training data set for mixed snow to see if I can improve these parameterizations. And the other thing that I'm showing here is the rollout mean absolute percent error for the rain moments mass mixing ratio to see. So the 3 different machine learning closures, the super drop net, which was that more complex machine learning baseline from the literature, the process rate MLP, which was the less complicated machine learning baseline from the literature. And then this is showing this neural ODE closure, which is still not performing probably as well as it could. We do see after retuning many of the bulk parameters, they're actually performing, most of them are actually performing significantly better. So the crosses here are the published parameters, and then the retuned are the solid lines for that particular data set. And I'm evaluating on a different data set from Mixno. So I think one question we can ask is like, what actually makes a good parameterization? Because just like having a parameterization that's the most accurate may not actually be our only ultimate goal. So we can think about all sorts of different axes that we can compare parameterizations on. So both accuracy and stability, how well it's physically consistent and conserves mass is important, but we also might care a lot about the complexity or computational cost, the interpretability, and the robustness of those parameterizations. So like the trade-offs that we might choose can depend on the specific application. And we can think about comparing like the kind of traditional parameterizations against the machine learning based parameterizations. So this is basically showing the rollout in terms of the mean absolute percent error for the 4 moments for collision coalescence. This axis that we could think of as sort of accuracy, and this other axis we could think of as like computational complexity. And so each of these different parameterizations like fall along this axis somewhere. So I think one thing that's interesting is that when we retune the typical physics-based parameters, even though originally some of the machine learning-based parameterizations can actually do better, we often find that retuned existing like simpler physics-based parameterizations can sometimes do as well, or at least comparably, and they're generally much less complex than some of the machine learning-based parameterizations. Although like machine learning does generally win on certain things which could be really important, such as the timing of rain conversion. So I think like this is something that we probably can think about, that like machine learning is not always the best answer for improving parameterizations. And there's still a lot that we can do with just retuning some of our traditional, more physics-based parameterizations. So I'll talk now just kind of like where this is going. The next step would be to actually try to integrate these updated parameterizations into a larger scale or system model, and think about sort of integrative and comparative evaluation across different types of parameterizations, as well as including other parameterizations besides just collision coalescence. So with LEGO ESM, which Pierre has been leading this development of this JAX-based or system model, we can look across a number of different like model hierarchies with the same JAX code that can be integrated directly. So we can look at both these like process scale benchmarks, as well as single column models, as well as running like this modular ESM and even coupled ESM experiments. So I think there's a potential to much more systematically with this approach, like much more systematically integrate it with these new JAX-based models that are being developed. So I'd say like the vision is that like with these tools, with both agentic AI as well as differentiable programming, I think we can move towards a much more adaptive and accessible system model development cycle, where we can have much faster iteration and we can have much more reproducible code. And this can also help lower the barrier to developing like new parameterizations and integrating new knowledge into our system models. So just to summarize, the outlook here is that physically grounded parameterizations for a system model still remain essential to provide interpretability, insight, and robustness for climate prediction. Agentic AI and differentiable programming promises to turn this slow manual cycle of parameterization development, integration, and evaluation into a more systematic closed loop. And some of the early results that I showed here is that agentic AI can reconstruct historic schemes in JAX. It can reproduce machine learning baselines with some caveats, and it can even propose some new physics constrained closures in JAX. Although, as I said, there are still some things to like continue to work out with this. So I think the outstanding challenges, like it's still to be understood, like how creative can AI be in actually improving ability to parameterize some of these processes. And there can often be very subtle or hallucinated wrong code. So this can create some challenges for trust and reliability. So I think we still need to think about like how we're really going to be evaluating these as agentic AI is used more for actually doing a lot of the coding. And we also need to think carefully and continue to think carefully about like the scientific validity of what we're coming up with. So yeah, thank you.
Hello. What was it? Were you so you when you retuned the traditional schemes, did you like use the fact they were differentiable now, or did you just do it by hand? Or it probably wouldn't make that much of a difference, but I'm just interested.
That's a good question. Yeah, it is using the fact that they're differentiable, that they're now implemented in JAX, which made it much like easier to do that retuning process, like also over multiple steps. So.
Yeah, I have a question about the last point about agentic AI help you propose new direction to try. Like in your experience, what are the main information that the agent was drawing from? Like it was reviewing the current runs and then try to, because the reasoning and planning is known to be challenging for untrained large language model. Do you provide them with like papers or
Yeah.
yeah?
So for like the neural ODE closure that I tried, that was like something that I suggested that it try out. For the when I was doing the API calls with Gemini, that was like I gave it access to mixed node data, but there were some challenges with giving it like complete access, like giving it all the data because there's only like a certain amount that can actually fit into the like sandbox for the API call. So I think that is still something that could be done more. Like that whole workflow could probably be set up to be a bit more like iterative and have like something like a knowledge graph that could actually help it like guide that process more.
Yeah, one thing I'm interested in looking into, which I learned from a business professor, is to think about like what is the in the box and out of the box. Like one thing, I don't know whether it's right here. One of the students we're working on is to think about whether is known to be hard for agentic AI to think, if they actually think. It's one way to structure it is to define neighboring thoughts for them.
Yeah.
Like we can discuss that.
Yeah, so like for the neural ODE, it definitely like was using the already existing historical parameterizations, like because it basically had access to that whole code base. So like use that in kind of reasoning out, like maybe we should try this rate-based parameterization approach. I would say like one challenge with that is also it kind of gets, once it starts going down a path though, it kind of gets stuck in that path though, because like it will be like, oh, this must be the right approach, even like when, for example, I would find like there was some like discrepancy with the data. So maybe the previous result was like that it judged something was incorrect. It would like still keep going down that path. So I think there were like having like hard resets to say like, don't like, I think there were some, yeah, there are still some challenges with it. It's like reasoning traces in terms of like, once it starts kind of going down one path, you have to be careful about like bringing it back. But
Hey, Kara, this was really neat to see. Thanks. I was one thing that crossed my mind when you were showing the attempt to mimic all of those five different parameterizations was the concept of, in the field, right, we're very worried about structural errors. So there's the parametric problem, but there's also how do we account for structures? And there's going to be many situations where you can't, although you have diagnostics, I say, well, this parameterization is better than this one. It'll be sometimes difficult, right? So have you thought about the possibility of, well, actually, maybe we can try to span structures as a function of common inputs and sort of have a parameter that's in there that sort of maps smoothly across and so we could sort of make the structural span into a parameter problem.
That would be interesting. I haven't tried that, but that was, I guess this was one of the things I was interested in, like which specific variables, like each of the different, calls we're actually using in their implementations, because like, but yeah, I think there's other ways also to think about visualizing it, but that's almost more like it's almost like a Cindy type approach or something, like creating like a library or something. That's kind of what you're proposing, or?
Not necessarily.
Grammar, like,
well, yeah, I'm not sure how you would do it, but But if you can do the sort of points, right, the different structures, then the idea is, and they all share some common inputs. They have different inputs, but as a function of their common inputs to the parameterizations, you should be able to get in between them, right? And then have a parameter that maps where you are, where you fall along that topography or that state space. So I'm just trying to think of like some of the pressing problems, which is just spanning structures and structural errors in models.
Yeah, let's just, I think this is like this like collision coalescence is kind of a good hello world example because it's complicated, but it's like not so complicated. Like, so we can actually maybe explore some of these things like iteratively. But yeah, I think that's a great point.
Thanks, Kara. Super interesting. I guess following up on Andrew's question, I'm wondering, like, when you were showing all the comparisons against different schemes and the retuning, in any of those schemes, did you kind of leverage in the loss functions or whatever refitting of parameters? Did you leverage like any of the emergent properties of these dynamical systems that is kind of like enabled by this auto-differentiability? I guess like, is this T10 metric tuned at all, or is that just an emergent property or testing independent?
It's tuned against these particular metrics, but that could be interesting to explore. Because like that, the conversion time cell is something that like obviously all the schemes sort of struggle with. So I think like maybe that could be an interesting thing to look into. It's just tuned against kind of like the bulk moments, like how well it reproduces those. But
Thanks a lot, Kara. Yeah, very interesting. And I think you really presented the future of, I think, what modeling will be in, and I think there was one thing that was very interesting is, and very much related to Greg's point, like how much you can push just the tuning of the parameters. Oftentimes we say pure AI models tend to beat like physics-based models, but I feel it's always like apples to orange comparison to a large extent, right? And you can really push the envelope of that and be very fair in terms of the comparison you're doing. So I think that's a huge advantage that you had.
Yeah, and I also think, I mean, like something like collision coalescence is a sort of, we could say, somewhat relatively simple process. Like maybe if you looked at something like parameterizing convection, you wouldn't get the same type of result where just tuning a very simple model would outperform, like at least when you think about also the accuracy versus complexity metric. I think like something like collision coalescence might be simple enough that we could get away with just these very simplified parameterizations, but maybe for something like convection, we do need something more complicated. But I think it's interesting to start thinking about putting these parameterizations on these axes and the different proposed parameterizations, because I do wonder if there's sometimes an overuse of some of the data-driven methods because we don't actually need that much complexity.
Maybe just one thing, I think there was something implicit in your talk, right? Oftentimes when we think about LLM, we say, okay, they are great at coding, they might be hallucinating, and you address that to some extent. You brought like benchmark data sets and figures in papers and stuff. But I think implicitly what we have is the capacity of those models to be multimodal, right? They can look at papers, they can look at code, they can look at benchmark data sets. And this is completely transformative, I feel. It's not just writing code. You can actually really start interacting with data, bringing all sorts of things, like experimental data. I even looked up some old papers that were just scanned, and then it was able to extract the data, like making some benchmarks. So I feel that this is really transformative, that part,
Yeah, I mean, I didn't talk about this all here, but I'm also have a project where I've been like using LLMs to read in like historical records to create like data sets for cloud seeding in this case. But like it's really been like transformative, not only to have the ability to read in the data, but also to like with Claude Code to set up like some extremely specialized like apps to review how well it's reading in the data, which like I think would be like it would take so much more time to do this, like without having that type of ability. So I think it's like really going to revolutionize how we can like work with some of the existing data sets too.
Thanks so much.
How key is having the expert in the loop, right? Because like you've been working on this kind of parameterization for a long time, you know what to look for, you know what to push back on, right? But somebody coming in doesn't know any of those things, right? And so we're going to get to a stage where people are going to be doing this without having any real expert in the loop. There'll be a human in the loop, but not an expert, right? And how are there ways of hedging against that kind of stuff? Because, if people start, when people start just producing a ton of these things, how will we be able to tell how good they are?
Yeah, that's
right?
a good question.
I mean, you're good, but like, I don't trust everybody else.
Oh, thank you. But I was thinking, I mean, I would say that the models can be very confidently wrong. That's one thing I've noticed. I think like there is adversarial review. Like Pierre has like noticed that like using Codex adversarial review on Cloud Code is like super helpful. So like so I think some of the reviewing one model with another model can be helpful for catching some of these things, but I do still, I don't know where the models will be in the future, but like, I think for what we're seeing now, they're extremely useful, but with caveats. Like we can't just fully trust. I think we can trust them to do a lot, and maybe we don't need to look in detail at every single line of code anymore. Like as long as they reproduce the types of metrics that we expect and that they look good on those metrics. I don't know, people are probably uncomfortable with that, but but I still think we are at a point where we're still having to do a lot of validation and a lot of checks to really make sure that it is doing what we expect in terms of like the performance of the ultimate models. So that is just my experience so far, though.
I just want to respond to what the Garvin said. That I think precisely because there be people, like you will not be able to stop people from doing that, right? Like you will not be, precisely because of that, what Kara is trying to do here is very valuable to scale up the effort of verifying and testing and evaluating all the wild ideas out there. Like the most beautiful thing about science is very inclusive, and anyone who have idea, no matter how new they're to this, have the permission to try. But what is also true about science is that we have to make sure that we rigorously evaluate every single idea before they can be deployed and then integrated into the system that will be used to make decisions. So I think what Kira is creating here is not only for her own scientific inquiry as a co-pilot for an expert, but also try to create something that expert can continue to develop into a scalable validation test bed before anything can be considered for production. I guess, like, fighting fire with fire, right? Like, and also, I think it's very important for us to have the tool to be able to fight fire. Otherwise, you have to build a wall saying no at all. Like that, I think that will not be a direction in the future.
And I think maybe also I think one thing that we've found is like when it has like if you're doing like say a code translation task, like say Fortran to JAX, where it can go back and compare like against an existing ground truth, I think the models and just kind of like letting the agents run on their own can do somewhat, like we can trust that a little bit more because it's got some ground truth that it can like iteratively compare as it actually improving against some ground truth, whereas like I think some of the things I've shown here have been a bit more like nebulous, like come up with an improved parameterization. Like there's not necessarily a ground truth. And I think that's where still like, have to do a lot of evaluation to understand like just how well it's actually doing. And if it's actually doing something useful.
Any other questions? Comments?
Thank you, Kara. Great talk. So it bothers me a little bit that the stability of the one implementation that Barry and Reinhardt was low in the human papers, and it was also low in the attempt by Gemini to do it. Is that because it didn't follow up with the second paper to know the 9 of 12 implementations that didn't work, and it was like borrowing those? It was searching back, or how exactly is it building these things up? Is it just copying things that have already been out there in the literature, and therefore it copied the bad ones as well, and that is why it is so unstable? Or is it actually like coming up with the pieces that go into the algorithm that make up that parameterization?
So I don't know if I can like directly answer that, but I would say the prompt that I gave it was like, here is the original paper PDF, use this PDF, but I could have maybe need to be like, more strict, because it probably does go and like explore, what it knows in its whole fact that those models have been trained on everything in existence that they can get their hands on. But like for this particular test, I did actually give it the specific paper PDF and tell it to reproduce that particular paper. So, but yes, I think these are some of the questions, like we don't actually know what it's fully doing. Yeah.
And then one more question. You mentioned that the human implementations were in general much simpler and that the ones that it had come up with were more complicated. Did I misunderstand?
No, not necessarily. This is just showing that like I'm just using the total number of lines of code it came up with.
Okay, so
And this is just like the red is what I implemented, and then the green is like what Gemini immediately implemented. So
then
it's comparable. They're not significantly different.
as we go through normal growing pains with the model, we have a new computer system and whatever new parallel processing, whatever. Those are these methods just as easy and portable to go through those iterations, or are they things that would have to be spun up every time? Like you'd have to like tell it to come up with this parameterization anew as you go onto different machines. Like I've heard from other areas, software engineers complaining that it's great, the one-off implementations a lot of these techniques come up with, but then when normal code updates, they don't hold up as well.
Mm.
Or
Yeah, I think
presumably if it's short, it's short, but
right. I'm not sure like I have an exact answer for this, but I would say with like working with Claude Code, you do have to like you can only work with it for it. You can't make the context window too long. It starts to like it can always go back and sort of access its history. And these are things that I think they're improving over time with like how these models work. And so it can like access the code base, but it's pretty useful to keep it having some like log of what it's been doing in terms of changes and stuff over time. It like often will like go back and look at the Git history as well. But it's like each time that you're running it, you sort of want it to be independent because it will start to perform worse after a certain amount of like calls, like because the context window gets too long, and then it's just like spending all of its time like rereading what it did previously rather than like coming up with like new ideas. So I think there's ways to help like how you work with these methods can help mitigate this, and also maybe having knowledge graphs or like more specialized tools that are developed for specific applications. But I think I'm not entirely sure. I think it is super helpful though for the ability that it has to go and access like the entire code base and like understand what is in the code is something which is really useful, because you can have it like you can make one change in a code and then it figures out like, oh, it needs to go back and make all of these other changes elsewhere. So I think like a lot of that type of logic, it seems to do quite well. So I'm not sure if I answered that question, but there is still a challenge of like having something which is, it's not fully like continuing to learn everything over time, because it almost has to like erase its memory after a certain amount of time.
All right. I think that's it. Kara, thank you so much for your talk.